ion problems is a very complicated thing to understand. So what common ion problem is basically that you start off with a solution, and so in this question you have magnesium fluoride has KSP of this. Calculate the solubility, the concentration of magnesium fluoride in 0.5 molar of sodium fluoride. So you start off with a solution of sodium fluoride that is already in solution, so the ions have sort of dissociated already. So you can see a bunch of sodiums and fluorines. What you're doing in a common ion problem is you're actually adding more stuff into the same solution. So in this case, we're adding magnesium fluoride. So what happens when this gets into here is that this is going to go into magnesium 2+, and then you're going to get more fluorines in there. So the fluorine ion, the fluoride ion here, in this case, is the common ion because it's the same one, okay? And the question here is asking, what is the solubility of that compound, the one that you're adding in? So to solve this problem, first you have to identify some concentrations. So what we can identify from this sodium fluoride is that if we were to write this in equilibrium expression, this actually breaks into Na plus fluoride minus. And this is the concentration, so it's 0.5 molar. Well, we can actually use stoichiometry to calculate the ion concentration of that. So this is going to be 0.5 molar and also 0.5 molar. So that's the concentration of fluorine in this NaF solution. So that's one thing. Second step now is your magnesium fluoride. So if we were to write this magnesium fluoride in your equilibrium expression, you're going to get Mg2+ and also fluorine minus, but 2 fluorines, right? Because you have 2 of them to balance this out. So one trick to know about doing common ion problems is that anytime you're given a KSP for a compound, that's going to be your ice table setup. So this is the setup. This is the ice table that I'm going to use it for. So I'm going to use ice table for magnesium fluoride, not sodium fluoride, because I'm given the KSP. So we're going to ignore all this. This is going to be your solid precipitate. So we're going to look at this. Magnesium concentration in the initial, since we don't have any magnesium to begin with, this is going to be 0. Do we have any fluorines? Yeah, we have fluorines started in here. So this is going to be 0.5. Okay, so that's my initial concentration, because when I put this in here, there's already fluoride ions there. That's your 0.5 molar. So moving on to the next thing, well, what's my change? Well, we don't know your change, so we have to use some algebra here. So you know that this magnesium is going to gain an X. Okay, it's going to gain something. It's going to gain a concentration of something. And the next one is, since this has a 2 of a molar coefficient, this is going to gain 2X. So then once we put this into equilibrium, magnesium is just going to gain an X amount of concentration, whereas your fluorine is going to have the same X amount, right? That's what you're going to gain, but you're also going to gain whatever is already existing in the solution, which is your 0.5. So this is already from existing, this is from your sodium fluoride, and this is from the magnesium fluoride, which we have to calculate. So here's the last step that makes it easy for everybody. So you're going to write out the KSP for your magnesium fluoride. So this is going to be Mg2+ times fluorine and squared. That's your KSP expression. Substitute all this in, so this is going to be your X, and then this is going to be your 2X plus 0.5 and then squared. Notice that this 2X basically took place of the 2 in front of this. So the next thing here is that this is the key step in common ion problem, because you're adding something in. This X is what we're adding in. In order to do this in a simplistic sense, we're actually going to assume that X is going to be 0, because we're going to assume the fluoride ions that we're going to add in actually is not going to play that big of a part. If we don't, then we're going to have quadratic, which makes it a lot more messier. So then if we assume that's going to be 0, that's this magnesium ion concentration is still X, so that's my X is still there. And then I'm going to be left with 0.5 squared. So then if we do the math, this is going to be X, this is going to be square this out, 0.25. My KSP here is, going back to the original question, 8 times 10 to the negative 8. So that's going to be 8 times 10 to the negative 8. And then solve for X. And if we were to solve for X, and I believe, where's my calculator? It totally disappeared. So let's see this, 8 to the power of negative X divided by 0.25. You would get 3.2 times 10 to the negative 7 molar. So this concentration is the concentration of magnesium fluoride in the 0.5 molar NaF solution. Okay, so this is the concentration of magnesium fluoride. If you were to look at your Le Chatelier, it actually does make sense because you're adding more fluorine in. So if you look at this in a Le Chatelier form, this is your NaF, right? This is the original that was existing. What you're adding in is more fluorine into the system, so you're going to push this down, which the stress is pushing this down, adding more of this, but your shift is actually going to make more of this product, or of the more product side. So this is what's happening in your Le Chatelier. If we were to actually calculate this in pure water, you can see that this number is going to be different than in pure water, but that can be left for another video. So this is, in a sense, what common ion is. If you didn't get what I was saying about Le Chatelier, just ignore that. But that's how you do for common ion. So try the next example, and hopefully this has helped you. So this is the second example for common ion problem. So this one involves with gold 3 chloride and has a KSP of that 3.2 times 10 negative 5. You're calculating its solubility of this in this solution. So you can notice that you start up with gold, you end up with gold. Gold is your common ion. So first step I'm going to do is I'm just going to break down and calculate what's my concentration of just gold. So here's my equilibrium expression. This is gold 3 plus. This dissociates into that. There's my NO3 minus, and I have 3 of them. So that's easy. I'm given 0.2 molars of this original amount, so I can use stoichiometry to calculate that. Well, I will also have 0.2 molar of gold. I don't really need to calculate nitrate because the nitrate doesn't really do anything in this reaction. It doesn't precipitate. Gold actually does. So I'm going to look at gold, and that's it. The next thing is set up my ice table. So because like I said from the last one, if you're given KSP of something, that's going to be your ice table you have to set up. So here's my gold chloride, and here's my equilibrium expression, so it breaks it down into this, and here's my ice table, and this is going to be ignored because it's going to be a solid, so that's your precipitate. So these are my AQs. So next step is, in gold, do I have an original concentration of gold? And yes, I do, because I'm putting it into a gold nitrate solution, and it already has a 0.2 molar concentration. The next thing is, well, what's my chloride ions? Are there any chloride ions in the existing solution? No, so this is going to be 0. So then what's my change? Well, I don't know my change, so I need to use algebra. So this is going to be plus x, right, for gold, and 3 for this one it's going to be plus 3x because 3 chlorine ions. So once you put all this together, so this is going to be plus 3x, this is going to be 0.20 plus x. Again, this is where this one is from the AuNO3 existing solution. Where this x is from, this is what you're adding. This is your AuCl3. So then once you have that, then that's the easy part. Then you're going to put your KSP is equal to Au times Cl minus, I should use square brackets for this one. Substitute all this stuff in. This is going to be 0.2 times or plus x times 3x cubed. That's going to be a huge number. Okay, so remember, in common ion problems, we're actually going to ignore this x. We're going to assume that this x is going to be 0. So assume that's going to be 0 because it's actually not going to play that much of a role. So this becomes 0.2. We can't assume this x be 0 because this x is actually the chloride ion. So we're going to have this, and if we multiply 3 times 3 cubed, this is going to be 27x cubed. So how are we going to solve for this one? We're going to go and plug in my KSP. KSP has a number of 3.2 times 10 to the negative 25. So solve for x, I'm going to divide by 0.2 first. This will cancel that. And then let's see what I have. So 3.2 to the power of negative 25, divide by 0.2. This is going to give me an answer of 1.6 times 10 to the negative 24. This is going to give me 27x cubed. I'm going to divide by 27. So that's going to give me 5.9 times 10 to the negative 26. This is equal to x cubed. Take the cube root of this, cube root of that. So then let's see what we get. You're going to get a very small number. It's a nice even number, so 3.0 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 times 10 to the negative 9. That's my molarity. What's the concentration of this that we just saw? That is my gold chloride. So this is my gold chloride concentration in a gold nitrate concentration. Okay, so this is my concentration in an existing concentration. So that's your common ion problem. Once you get the hang of it and you do a couple of them, it is actually not too bad. It's just in the beginning where you have to set it up. That's where it gets a little bit tricky. So hopefully this video and this example has helped you. So see you next time.